So I'd like to talk about Kirchhoff's voltage law in this video, and from one of our previous videos we defined current. So current is defined as the time rate of change, the time rate of change of charges. Okay, so mathematically I, which is the current, can be written as time rate of change squared to t, and the time rate of change of charges. And equivalently, we can write Q as the integral of the current. Okay, so here I use x as a dummy variable. Now, so what is the unit of the current? So the current I of t is expressed in amperes. Okay, so in amps, which is coulomb, so in SI unit is coulomb per second. Okay, now although we know that current flow in metallic conductor, right? So current flow in metallic conductors, okay, is due to electron motions, right? So it's due to motion of electron. Okay, so but it is widely accepted, it is universally adopted that the current flow is represented by motion of positive charges, that current flow okay, is represented by the motion or movement of positive charges. So that means what? So when I have a piece of conductor here, okay, so when I have a piece of conductor, when I have electrons, okay, so when I indicate that this is the direction, or this is the conventional direction of the current, then the electrons, right, are going to flow this way instead, right, in the opposite direction. Okay, so it's important that we keep that in mind, that you know the direction of the current indicate the motion or the movement of positive charges. Now I like to define voltage. Okay, so what is voltage? Voltage between 2 points. Okay, so I would like to give you those definitions, and then I'm going to use that definition to define what we call the Kirchhoff voltage law in a minute. Okay, so we know that the motion, so we know that motion or movement of charges, right? Yeah, energy transfer. Okay, so voltage between 2 points A and B. So voltage, so between 2 points A and B in a circuit, okay, is defined as the difference in energy level of a unit charge located at each of the points A and B. Okay, now KVL, right? KVL is defined as the algebraic sum. So Kirchhoff voltage law, okay, is defined as the algebraic sum of voltage around any closed path in a circuit equal to 0. Okay, around any closed path in a circuit is 0. Okay, so why is that so? I mean, yeah, I'm gonna use the definition that I gave you above to kind of justify that. Okay, so a closed path or a loop in a circuit, so let's say you have a circuit, we can just arbitrarily select a node, and then we can trace a closed path through some element in the circuit, and we're going to return to the original node without passing through any intermediate node more than once. So when we have that, then we call that a loop, right? A closed path. Okay, so now, so let's say that I have this point A, B, C in, so A here, B here, C here, and I have a charge Q, okay, and let's say that I'm moving Q around this loop, right, this path. Okay, so from my definition above, the energy, the total energy, expanded, moving this charge around this loop, right? So we have the energy will be Q times the potential at B minus the potential at A, and then Q times the potential at C minus the potential at B, and Q times the potential at A minus the potential at C. So the total work that we have will be equal to Q VB minus VA plus Q VC minus VB plus Q VA minus VC. So when I pull the Q out, I have VB minus VA plus VC minus VB plus VA minus VC. So you can see for yourself that so this cancel out with this cancel out with this, and this cancel out with this, and this becomes Q times 0, which is 0, right? So that means VAB plus VBC plus VCA is equal to 0. So that's what we indicate above, and I use the energy, right, to kind of justify that. So the Kirchhoff voltage law says that when we go around this path, right, and I come back to that path, we start from node A and then we come back to node A. When we sum the voltages along the path, we should get 0. Okay, so that comes from the conservation of energy. Energy cannot be destroyed or created. Okay, so so when a positive, so let me write it down. So a positive charge, right? A positive charge. So again, energy. Okay, as it moves, to a point with a higher voltage, okay, and release energy as it moves to lower voltage, as it moves to lower voltage. Okay. Now, so let's do an example. So before we do an example, I would like to talk about, we have been using this, but I haven't really talked about them, right? So basic component in a circuit. Okay, so I would like to talk about sources first. Okay, so I'd like to talk about independent sources. So which is voltage source, right, and current source. Okay, so an independent voltage source. So if I have this, is a two-terminal device, right? Two-terminal component that maintains constant voltage across it, regardless of the current through it. Okay, so if this is 10 volt, the value between A and B, the voltage VAB, which is VA minus VB, is always going to be 10. That's the potential difference between those 2 points. Okay, so what about a current source, independent current source? So current source, this is the symbol, is also a two-terminal device, is a two-terminal component or element that has a constant current to it, constant current through it, regardless of the voltage across it. So if this is A and B still, regardless of the voltage across it. Okay, so if this I go to let's say 2 amps, then the current will be 2 amps, will be constant 2 amps. Now, so let's talk about dependent sources, right? So dependent sources. So we're going to be voltage source and current source. So let's do voltage control voltage source. So you have voltage control voltage source. So voltage control voltage source is given by, so this is a voltage source, and the voltage across this dependent source, right, this voltage, right? So when you see this diamond shape, right, so that represents a source that depends on voltage or current somewhere in the network. So I will have this voltage source depends on current and depends on voltage. Okay, so that means the voltage across this will be some mu times, right? So let's say alpha times Vs. So this Vs, so remember alpha will be just a constant, right? So it's a constant. So that means somewhere in this circuit, right, we have Vs there. Okay, so then the voltage here, which is Vs, the source will depend on that Vs. Okay, so if I call this A and B, now let's do the same thing here, A and B. Okay, so this will depend on a current. So that means we have a current somewhere in the network, and let's say this is IS. So then this voltage will be beta IS. Okay, so that means this is a current somewhere in the network. Okay, and this the source, so this will depend on that. So beta also here will be a constant. Okay, so I'm going to elaborate more on this, and let's say let's current source. Let's talk about the dependent current source. So dependent current source. Okay, so we have, as I indicated above, dependent source. Let's say we have a current. This is a current source. Okay, and this current source depends on some voltage somewhere. So because it's a current source, I will be equal to beta times some voltage Vs somewhere. So similarly, we have some circuit here, some component here, and the voltage across that component, we call it Vs. And that depends on Vs. Okay, and then I have this current source that can depend on the current somewhere in the network. So I will be some alpha IS. So IS will be current somewhere in the network that the source depends on. Okay, so this is A and B. So we have so for now we know the passive components that we talked about so far. We have the resistor. All right, we briefly talk about the capacitor and the inductor in some other videos. And there's sources. So in the next video, we are going to give examples. Where we will apply Ohm's law, KVL, and KCL will be applied. To solve for current and voltages in circuit. So please follow me in the next videos. Please subscribe to my channel so you'll see you'll receive notifications when these videos are posted. Thank you.